Hey everyone, and welcome to the SaaS developer community where we discuss how to build SaaS and learn from each other. And with me today, I have a brilliant guest. I have Dr. Anna Povzner, who is Director of Engineering at Confluent, and she and her team just won the VLDB Best Industry Paper Award for the papers that described Kora, the cloud native platform that they built for Confluent Cloud. So, Anna, it's so good to have you on the show and just discuss the paper and all those cloud native learnings.
Yeah, hi, Gwen and everyone. Yeah, I'm very excited. And also because, Gwen, obviously you were part of it when you were at Confluent. And also, obviously, thank you for helping kind of drive the vision and all the input you did. So it's also your win, I think, as ours. But yes, very, very exciting to have it VLDB and also as a best paper.
Yes, Anna, you're extremely kind to me, but I think even when I was at Confluent, it was very much your vision. I am never going to forget how day one, when I joined the team, you told me, our mission is that customers will give us their workload and the credit card, and we will take care of the rest. And this has been pretty much my motto about usability from there on. So I think that's pretty much what Kora is all about, right?
Exactly.
One of the things that I think caught my eye when I started reading the paper, very early in the first paragraph, you said that Kora is the cloud native platform that is driving Apache Kafka and Confluent Cloud. And then you said that this paper discusses the design and the abstractions. And it's pretty rare to have one of those papers really put abstractions and design at the same level. And it really was kind of, why are abstractions such an important part of what you did?
Yes, good question. Exactly. I think abstractions is pretty much like a key, right, for that cloud native experience. And one thing if you think about if you want to host your Kafka, say in cloud or any actually system, you have to start thinking about lots of things, and it's very complex, right? You start thinking like, oh, how many instances, what instance type, what storage class. Even like you're looking at like one cloud provider, there is lots of choices, like both on cost and like other like performance characteristics. Like one example, like on block storage, right? You can choose one, you have a fixed IOPS and throughput, and then you have some kind of burst. Or the other option, you can choose like configurable, also IOPS, storage, throughput. So there's lots of things you need to choose. And then if you talk about like multi-cloud, right, you can start thinking like all different core structure, like it's a lot of heterogeneity. And so if you start going that deep, like you're going to spend lots of time. So in practice, right, if you go to cloud, what you really want is that like you think about your workload, about your business logic, like you don't want to really think about that complexity. So that's like one big thing. But I would say another, really, I would say win-win for both, our users and actually, us as a hosting, building Kora is that, once you have that good abstraction and the good, your contract, right, then you underneath, you can start doing all the optimizations, because constantly, right, hardware changes, software changes, maybe, we learn something and now like, oh, we have this great idea, like say change a file system. And so that, right, so we can do all that stuff in the background and, we just keep our contract and we constantly deliver this continuous optimizations. And we give it back to our customers. Which is very good, right? For both, because like what it means, like, when we do that, when we optimize how it looks like, especially like say, like you have a dedicated offering, right? Whatever you are still, buying and what you are actually getting when you're provisioning your, Kafka in cloud, you're getting your, what we call like, you basically reserve like units of capacity, right? And that unit of capacity kind of defines, just be kind of given this contract, you get this bandwidth or specific workload, maybe characteristics, but that's it, right? And it will be unified across all cloud. And then, we basically, it's our job then to deliver, this unified experience, predictable performance and all the, optimization we can get.
So what I'm hearing is that having the right abstractions enables you to innovate without your customers having to jump through hoops in order to enjoy this level of innovation. What are the abstractions?
So abstractions, we have the main thing is actually just, as I mentioned, you kind of have this, what we call unit of capacity. We call it CKU, but it's pretty like a Kafka unit of capacity. It just defines your a minimum cluster size and also minimum kind of size that your capacity that you can kind of expand and shrink the cluster. And that basically, and the way you describe it, it's like you can get certain amount of bandwidth from it. There are certain dimensions that we, kind of describing workload, right? Like connections, partitions, requires, but there's not many of them. It's just few dimensions that you just need to kind of describe that what you can fit, and that's pretty much it. So when you kind of provision the cluster in cloud, you just say, okay, that's many CQs you need, but then you can also expand and shrink it. So that's pretty much what you're choosing. You don't really need to think about no other details.
And then you really took this abstraction, which talks about capacity units, and you applied both to dedicated clusters, and more recently, you also have, I think I saw Confluent launching the eCKU for the multi-tenant clusters, right? So the abstraction now applies everywhere.
Exactly. Although it's actually multi-tenant is actually much, I would say, there are some, and even a bit easier because, the abstraction here is more like, in dedicated, you still kind of, you have your actual physical resources dedicated to you. So still you kind of, in a way, you kind of reserve it. But in ECKU, it's really just a unit of, how much you get billed, but it's not really a reservation because you share, there's a multi-tenant setup where you share with different other kind of that logical cluster, what we call. And so, yeah, but the abstraction is actually the same. You still kind of know that this is kind of the unit you're getting. It just, you even know
this capacity can be the capacity I reserve or the capacity I actively use at the moment in time.
Exactly, yes.
Yeah, that is a very useful abstraction. So one of the things I saw in the paper was you started out by listing the design goals, as one does, and it struck me that there were a lot of them. Elasticity and availability and durability and multi-tenancy and all those different things. Did it ever get hard to just reconcile so many goals into one system?
I think yes, although I would not say, I'm just thinking back and maybe I could forget, you pretty much try to deliver on the goals, but it's not mean that they're really against each other. But you do need to have lots of choices actually to make that happen. And for example, we're listing, right, the performance as cost as two different things, but it's a continuous, I guess, struggle, but let's, or, challenge of how do you have this optimum cost performance? So lots of your decision kind of driven by that. Right, so that's kind of one angle because they always kind of interact with each other, and that's when we're talking about when we had to do tier storage to to make sure that you can two-tier storage so you can actually get there, and we're talking about abstractions, right, that we can get there. So just doing that, it's already complex. But multi-tenancy, I think, availability, that's challenges because multi-tenancy just provides so much more complexity. So you need to do much more work to get this isolation, to get availability, right? So it's becoming, I would say, and multi-tenancy is a big kind of feature to actually get you that cost efficiency back. But then it's much more challenging to achieve the goals. It doesn't mean they're not achievable. You just need to do kind of more and more effort to get there. And then I would say latency, I know actually latency is more related to why it's hard. It's more, I'm not sure we listed, I need to look back, but the driver of of the design also comes from that ability to handle all these variable workloads, right? Because in cloud, you don't know what the workloads are unpredictable. They're very, very changing. Multi-tenancy add another complexity because then you imagine you have all these different potential users, they have different workloads, so that variability becomes even bigger. And that variability make it harder to deliver latency, because you continuously need to keep that cluster very well balanced, right? Because anything like you not balanced, then it brings to your P99 latency, which what customers usually care. So they all kind of interact in a way, right? Something makes it more challenging, and it's really just more effort to get there.
Yeah, that makes a lot of sense to me. So basically, it's not so much as there are trade-offs as much as you had to deal with all of them at the same time and build a system that solves for all those constraints, essentially.
Exactly. And it's kind of like, I think you've seen it, right? They're like, you're kind of thinking, okay, what's the common cases? But there's so many use cases, and more scale you get much more, and then like the corner cases you consider becomes very common again, and so that's where challenges come from.
Yeah. So I'm trying to think about like taking even just performance and cost. Obviously, it's very easy to give high performance if you don't care about how much you cost. It's very easy to lower cost if you don't care what happens to performance.
Yeah.
But then doing both cost and performance optimization is still not extremely hard if you know the workload. But of course, not only didn't you know the workload, you even had clusters that the multi-tenant ones, the workload is extremely unpredictable by design. At any point in time, anyone can click create cluster, starts producing, starts consuming. You have absolutely no way to start planning for it. So how did you deal with an architecture that really needs to be optimized for anything?
I think there's lots of answers, because basically N goes to that. I think one is kind of keeping, that whole kind of life cycle of, keep it at making sure it's balanced. You react, to new workloads, and you be able to like quickly kind of expand when you need to get more capacity to protect your cluster, to make sure you're isolated. So kind of that thing has to happen. So I can a little bit talk more about this. I think it's really interesting.
Yeah, maybe we should just walk through an example. Like, let's say that I join Confluent Cloud, click on, I want standard or basic cluster, and it says up to 100 megabytes per second. So I'm starting to spin up producers and send data your way. What do you do next?
Now it's 250, 750 megabytes per second. It's 1 gigabyte.
Sorry, how much?
Old news. So it's 250 to 750 megabytes.
250?
250 megabytes per second.
And 750 out.
Yes. So pretty much like 1 gigabyte total. So we already made progress.
Whoa, okay. So let's say I'm trying to do that.
So, and obviously scaling, having the higher limit that you can scale, obviously make it more complex. But yes, and actually, I want to say like, you kind of, that's like from one perspective, but like when you say multi-tenant, right, we actually have like clusters in popular regions which have like thousands of tenants, and the ones like and right, the fact that you can actually create a cluster and just like kind of keep it there until you run the workload because you're paying for what you're using, it means that like you have all this potential like tenants which sit there doing nothing. We actually had, what's funny, someone in my team called them a sleeper agent. So they sit and suddenly can just like come out. So generally, because of multi-tenant, because of economy of scale, we do keep and quite some headroom. So it's not that like one tenant comes up and suddenly like you need to like quickly react. So we do have extra capacity, but it's always statistically, it always can happen that suddenly just like you need more than you need. But generally, even if one tenant, right, need to scale right away, right, it's not guaranteed that like you nicely just distribute all your load across all the brokers and like it just good, right? Often it's like you don't know, you can just have more loads just come to one broker, and it just come from that Kafka model where, right, you just writing to like, you need basically writing to brokers or reading where you have replicas, right? So depending where your data, you need to
so for example, if I use some kind of partitioning key, and a good example sometimes is the stock market. There is a lot more Apple transactions in any given day than most other stock. And if I have a partition for Apple, or even a partition for A, which has Apple and AT&T and all those, it will be one broker taking a very large chunk of my stock updates traffic.
Exactly. And so if you do that, so obviously we do have all the protections, right? We do actually set, like, each broker have protection like on bandwidth, because we always need to make sure there's enough space for applications. So you always data, you don't lose any data, but then protection on just not being overloaded in queues. So all that happens, right? But it's not a situation when you want to, it has to be very, very short and temporary, because then your latency, any throttling kind of increases your latency. For some application, you can be really, really sensitive to that. So it's kind of like you need to have those protections, but then you need to quickly also our balancing algorithm have to quickly react and start rebalancing. And that's where the two-tiered architecture important, because we don't want that much data to move around. So that's where that comes in. And then you also, if you don't have enough capacity, because we don't have to keep that enough buffer, you need to start scaling. So all that needs to start happening. That's not even all it, because this also kind of applies to in the dedicated. You also have all this situation when you need to have the isolation between tenants. And so obviously we have all these quotas. We talked a lot, we have a bunch, even our blog post talked about it. So we do protect all the resources, tenants between each other with quotas, but it's always interesting, what happens when you suddenly not have enough capacity. Then, you need to make some hard decisions. So we have all this, mechanism with auto tuning. I think we talked also. That's we did a while back, that we just make sure, when you don't have enough capacity, you quickly squish everybody quota. You provide, some kind of fairness, but then you quickly have to have this. Get back to your enough capacity.
Yeah, exactly. So as you said, the application of quota has to be temporary, because otherwise my application will suffer.
Yeah.
What do you do next?
Exactly. So, and that's pretty much basically balancing and then expansion, right? All that elasticity have to just take place, because you continuously need to try to make enough space for everyone. Right. So that's basically what
And
happens.
do you and sorry if I'm asking for details you can't share, just tell me.
Yeah.
But do you only start by applying the balancing processes when someone spikes or when a limit is reached, or is this something that just continuously you are trying to optimize workloads and shift things around?
I would say it's more a bit in between, because it is continuous in a way that we don't want to go to the bad state. So, right. So I'm only talking about actually, that's a really good question, because I realize it might sound like we always wait till the end before you rebalance. Actually, that's not true. So that's a kind of a worst case. I'm a very worst case scenario, have a worst case scenario thinking. But in practice, right, if you have start getting imbalance, we continuously rebalance, but we need to be also careful. We don't just rebalance for the perfect case, because rebalancing itself is overhead, right? Even just thinking, of course we do keep enough just capacity for rebalance, but rebalance is also somewhat a bit of disruptive, right? Because you're moving replicas, the metadata needs to be updated back to client has to reconnect. So you need to also be careful that you don't rebalance as often. So we keep that, basically we have certain thresholds, so we rebalance before we get to that situation, unless somebody spikes, there are certain corner cases, but we do rebalance, but just not trying also kind of not to get to that place when you just the oscillation, right? You're continuously moving stuff. So you don't want to happen.
One of the things you kind of mentioned, I think one of the things with the paper, it goes over very much breadth, so nothing is super deep. But when you mentioned the dynamic distribution of quota, that's between tenants sharing a broker, or is it something that is more between brokers as well?
Oh, it's between brokers. So it's actually pretty simple concept. And I think it's also been already, it's a known technique, I think, in systems, right? It's really more about obviously you give certain limits to the workload, right? Like say when you buy, as we mentioned, you buy like some standard basic cluster, you buy up to certain bandwidth, right? So we need to have these limits to kind of at some point stop you from using like the whole cluster. So that's like one limit for your whole, logical cluster. But in the end, right, because Kafka is a distributed system, you need to it's still things happening per broker. And so we need to give certain like what we call slices of that quota to broker. And like early days, and that we had this most simple thing, let's just make it static, like let's just give certain same slice on broker, but it doesn't actually work, right? Because we don't want to make a case every say tenant using exactly same per broker, they can be different, depend on usage. So dynamic quota is basically been more kind of relaxed. We're just making it's kind of like more flexible. You want this, use this resource in the broker, you get it. But of course, if we start kind of having issues with other tenants, we start balancing. And then it's really much dynamic, meaning that it's constantly kind of looking at your usage, and then if you need it, kind of changes, because you still need that kind of somewhat central place that that overall you're still not using too much resource in a cluster overall.
I think I got it. Yeah. Another thing that you kind of mentioned in the paper that was very interesting to me is that you're using a cellular architecture, which is, I think, something that only now has really become kind of a popular best practice that everyone is talking about and discussing. And it used to be almost like the best kept secret of large providers. Can you share a bit about why you went in that direction and the benefits you got from it?
Yes, so that's very interesting, because we actually learned, and I think this learning can be even applied to even on-prem systems. And it's the one part is, right, the use case that we have is multi-tenancy, that you essentially have a smaller tenant, that smaller meaning in capacity needs, that would run on much bigger physical cluster. And normally in Apache Kafka, you have the mechanism to kind of place partitions on when you create a topic, right? You basically distribute them across all the brokers, because the idea was that you want to get much parallelism to get the best performance. And it's mostly was, I guess, designed when it was more static system, maybe less kind of workload or maybe application on a system. But what happens, right? So one thing is even if you think about really large deployment, even on-prem, if you have this that central nervous system, right? That you have the central pipeline, the Kafka that's used by many teams, application essentially is also multi-tenant. And then, if you start, if you need much smaller capacity, but then you essentially spreading the tenant across all the brokers, then every broker just hosting every tenant, it's just not very good for just reasons. You just even say, some storage degradation happen on a broker, right? You're kind of losing temporary capacity, and then every tenant impacted. Or something happens some workload, some doing some weirdness, and maybe you have some isolation gap, then you impact everybody. So you don't really need to do it. So that's kind of was our original actually reasoning, that, you don't actually want to spread all the tenants thin on every broker. You want to actually kind of try to put them in a smaller subset of brokers just for isolation. But the other interesting observation that, which is now when looking back, I think it's very, obvious, but it was not obvious, I think, at the time, is that, even for performance, you really want to spread partitions in just enough brokers to get enough what your performance you need. But once you start adding more brokers, you're moving partitions, then what happens, every client has to connect to every broker, then you have less batching, so you're kind of splitting your request, and then you're essentially adding more brokers, you're actually adding more load.
This is such a huge point. I mean, we've seen so many cases where people kept adding brokers, and why isn't my performance improving? It's because you're, after some point, you're also adding overhead, as you said.
Exactly. And so sometimes like you can see like, oh, actually, why do I have more load? Like I have bigger cluster, but more load. What's going on? And it's only because your requests and connections taking resources. And so we're like, actually, you don't want to you don't want to add that. Ideally you want to have just enough brokers, but obviously like it will be too complex just to do it. But that's where cellular architecture helps. And what it is just you say, okay, there is like set of brokers, it's a cell, and that tenants would kind of stick to that cell, but not permanently, because of course you can move if you need capacity, but it's more about kind of trying to constrain to your tenant and less brokers. They will still share, but it's less sharing, but also it's good for performance. And actually in the paper, we have provided results of one benchmark. We have details, but we actually saw a 20% improvement, going from no cells to cells with the same workload, which is like, that's actually pretty big. We did not expect that.
I think few months before the paper was published, I think it was maybe in May, I was in a conference and I talked to someone. He told me about, I don't even remember the company, but they told me about how they were struggling as their Kafka cluster became bigger and bigger. They are cyber companies. They ingested a lot of logs. It just kept growing. And then they solved a gigantic list of problems that they had by moving to cell-based architecture. And he was so upset. Gwen, why doesn't anyone talk about how you can solve all your Kafka problems by moving to cell architecture? Why aren't you telling anyone? So now you are telling people.
Okay, yes, exactly. I was also that like, and we're learning this where like actually it even makes sense. So just like multi-tenant is in our multi-tenant offering, but just any large deployment, like you don't need to, right? Because you even want to kind of isolate your applications and make them more performing. So
Exactly. It really is a best practice for very large clusters. And I think something that has been under discussed so far. So I'm glad the cat is out of the bag. One thing that people always expect from cellular architecture, and I think it's partially because AWS talks about it a lot when they discuss cell architecture, is that cells will also increase availability. They often call cells availability zones, fault domains. They have a lot of terms that imply that you shouldn't be thinking just about performance or even at all about performance. It's all about availability. Have you seen availability improvements as a result?
Oh, definitely. And it actually was like, that actually initial reasoning to move to cell. So performance was not, I guess, initial for multi-tenant. It was really more availability and specifically that blast radius I'm talking about, right? Because anything happens on, say, one broker, it just then every tenant is impacted. So once you go like, basically like any issue, and obviously like in cloud, like lots, the failure is very common. It's more that like now, any failure, the impact is much more contained. So you see that of just generally availability. And yeah, so just make like much less, tenants also to impact each other.
So let me switch topics a bit from the paper and really ask you, it's very clear that you solved really hard problems. Like you had a lot of constraints and you didn't really trade them off as much as may figure out a way with a lot of really challenging to implement components that basically answered all those trade-offs. And we talked about some of the components that are hard, like the quota system that is kind of complex in its own right, the balancing system that is complex, cells. We haven't talked that much about tiered storage, but that's a very critical base part of the system. All of those were really big and deep investments. And something that you don't always see in technology companies of Confluent size. Like you see more of it in, giant companies that is literally printing money. They can fund all those really deep projects. Like, Google comes to mind. How did you get and give the team the space to really dig so deep on such a hard problem without any trade-offs, any shortcuts?
I mean, it's not completely in the way like we did incremental, right? Improvement. So it's not necessarily that like, we didn't like, what do you mean by shortcut, right?
Yes.
But on the other hand, I would say like it's not that like extra, right? It's really like because our system needs to support like all the mission critical workloads. It's a requirement actually to deliver those, and especially on availability, all the even cost effectiveness, right? That we actually have customers, like all that in a way, it's actually a requirement. But you're right. I think the part we're doing innovation, and there is much more improvements, in the pipeline, and a lot of this also kind of making sure that people have focus sometimes, right? It's like, sometimes you make like, you do all your, like, we still also operate all these big clusters. So there is lots of like things you need to do daily. But actually, I would say normally when we actually did a good progress and made that happen, it's like, you have some small teams kind of really moving ahead and delivering that. So I think focus, like I would say, like one of the biggest things there to get.
It's interesting because really when it comes to engineers really doing those deep technical innovation, there is two factors that are involved and can sometimes help drive the innovation, but can sometimes hold you back from doing this innovation. One of them that you mentioned is the operational load. Like sometimes because you see all those problems in production, you can think of really interesting solutions, and it's easier to buy the organizational commitment to solve them because the pain is so obvious. The other factor is features. As you know, there's always product managers, they always want to ship cool new features. And sometimes these features can come at you want to ship features fast, it can come at the expense of doing this really deep, really innovative work, especially when it's actually harder to explain to the customers why it is so cool.
Exactly. And actually there were times where we're just saying, okay, let's make sure, like, especially if we are getting to a place when like we have more of that operational load, we actually sometimes do stop, or not fully stop, but we kind of focus more to kind of more go ahead and get to the better, the system. So we actually, and thanks to our leadership as well, right? It's all about how how we prioritize. But yes, we do have those parts where like, okay, let's just make that system better in terms of like getting the availability, all those main metrics that actually customer hears, because that's what they care more than like features potentially. So we do that. So then we kind of don't get to a place when we fully reactive. Only thing we're doing is just like
this is something I heard from Confluent leadership a lot. Yeah. Customers don't care about your cool new feature if the system is down.
I mean, in practice, that's true. And in the longer term, it obviously improves, right? Because in longer term, like you kind of maybe like push to like get the things to a better place, and then the longer term that you have time to also focus later, right? So you don't have to that context switches. Yeah. So definitely that's like, I think it's a big deal.
Since you and your team spent so much time at the really intersection between on the cutting edge of Kafka performance and your customers, one question that I think is still not settled is how much do Kafka users actually care about performance? And, now there is obviously Kafka in Confluent Cloud and some other vendors. There is also vendors that say we are much faster than Kafka. There is also now vendors that say we're actually much slower than Kafka, but we're better in other ways. Where do you see the spectrum in terms of the customer needs that you get more exposed to?
I would say pretty much all the spectrum. I'm not having a specific percentage, but that's very true. I mean, there are some customers or it's like actual application use cases where like you need a super low latency, and any like big spike can basically kind of like appear as an availability, especially like, there is a big, kind of pipeline of application happening on up the stack, right? So like how they designed, like it's also, of course, like partially it could be like the way it's designed, but still like any like even reasonably what some application might not even consider a problem, some application actually do. So, and those would be like, if you don't deliver it, then it's like actually not usable for them.
And it sounds like Confluent Cloud does deliver those.
I mean, that's like one of the big kind of drivers, and I think in current you will hear more. By the way, next week, we'll have some more kind of like talks on like how we actually we did lots of effort into like kind of delivering good latency.
Oh, so your team is doing talks at current about
Not my team. There is other team, but yeah, there is some.
the paper. Some of the paper authors are giving
Yeah,
talks.
exactly. Yes.
Amazing. Oh, so you mentioned applications that get consecutively slower and that react disproportionately to very small spikes in performance. I want to share. I recently learned that in the front end and web development world, they have a term for it. They call it the waterfall pattern, because if you look at observability and you have those spans, when I started an operation, where I finished, it kind of looks like a waterfall. The idea is that you make one call and then you need to wait for the response, and only then can you make few more calls based on that response, and then you get all the other results. And it's kind of obviously all this back and forth until you finally get the thing you really need. Any latency spikes obviously has huge impact because it slows down everything that comes after this request that just spiked. So yeah, just sharing that waterfall pattern is considered an anti-pattern in application design. Don't do it.
Exactly. And also, I think the part is not just the latency, right? Because on any levels, right, latency can cause certain timeouts. And so any timeout you have to retry. And it's basically, I think that's one reason it could just appear as an availability at certain level.
And you know, this is actually not just that it appears as availability. One of the very basic tenets of distributed systems is that we don't have any way of knowing the difference between timeouts and unavailability.
That's actually very true.
The definition of timeout is of not available is we waited long enough and it still didn't respond. Mm-hmm. Will it respond in a few days, in a week, in a year? Who knows?
Exactly. Yeah, I think actually appearing probably here wrong word, because it's more from perspective as a us provider of Kafka or Kora, right? Like we actually right, our cluster is all up, everything is healthy, potentially be latency spike, but and suddenly the actual user like, oh no, it's actually not available, so you don't even see it. So that's also
as a client, you just have absolutely no way of telling the difference between something that is extremely slow and something that is not available. And another very common saying is that those nines don't matter if the customer is not happy.
Exactly. Yes.
Cool. So I always finish the conversations by asking for tips and advice for people building software as a service applications. So if someone is writing a software as a service applications and wants to use Apache Kafka for events, which is a very common pattern, any tips and advice in addition to use Confluent Cloud? Maybe tips and advice to people already wanting to use Confluent Cloud.
Okay, let me try. So I think first of all, I think needs to be kind of a bit careful with the kind of configuration. Like I think it's very simple advice, I guess, right? Like try to stick to default until necessary, because sometimes I see very interesting choices. Like one very good example, actually, go back to timeout, right? Sometimes I notice, people would set like, let me set a shorter timeout, hoping that something will finish faster. I've seen this before, and actually, obviously, it's not true, because if something is slow, then you just basically have your timeouts reconnect. So resend your request, it's just gonna be worse. So like basically, don't use timeout or small timeout as a config.
Small timeout is not going to get anything to respond faster.
Exactly. So I think that's like one big thing. Like you kind of see it. I think generally the other part, like the pattern, which is like not really doing anything good for you, is when you basically, to send any request to create a new connection. We've seen it, and sometimes there are certain languages which is like kind of make it not clear, so you can actually accidentally do it, and then you pretty much you can end up with like really large cluster delivering very small bandwidth. Because the only thing you do connect in sending requests. So that's like another like really bad and like anti-pattern.
No, those are all really good advice. Absolutely. Yeah, I think the timeout thing, it's very subtle. I think if it really depends on what you want to do when it times out. Because if the thing you want to do when it times out is retry, as you said, it's not going like timing out and retrying is not going to make anything any faster. If anything, the opposite. On the other hand, if you're worried, hey, if my timeout is very long, then a user will be sitting on the screen waiting for a response. They will not get anything. This is really bad. I don't want them to sit waiting for that long. Then you may want to time out sooner and give a response to on the screen saying, sorry, the server is busy at the moment, come and begin later, kind of thing. So if you're not planning on retrying in a loop, it actually may make sense to time out a bit sooner. But yeah, obviously software engineering is flexible. You have a lot of techniques on how to deal with the fact that right now the server is not responding. Anything is better than spamming your server. It's just going to get slower.
Exactly, because like this, like we've seen very like interesting interactions, right, between like, especially when you like overloading, especially like if you think about like your own deployment, right, like you start overloading your cluster, you can even set all these quotas and throttling, and then it can interact in a way that you just continuously reconnecting and just spamming, basically DDoSing yourself. And then like and I think the other part is generally, I think like timeout is like one of part of this kind of bigger, I would say, advice, right? Because like in Kafka, right, it's you can the way you design application can impact how much resources you need, like how much say instances, because you can do it so well that like you just very efficient in bandwidth, like you have minimal CPU, like requests and connections and everything. Wow, you can design it in a way that it just completely just uses a lot, and you need to kind of just be more careful on like batching. And that's actually, I'm just thinking about that, kind of comes back on that the blog post I wrote a while back on tail latency, because really that's what defines your performance, and better you design your workload, it kind of gets you a better latency, better like utilization. So it's all kind of connected.
Anna, thank you so much for joining us and sharing a lot of in-depth knowledge and good advice. I have to say, I will have to listen to this conversation a few more times just to make sure I really got all the points. But it was really fantastic. I appreciate the conversation.
Thank you, Gwen. Thank you for inviting me. I never been to your podcast. It's very famous, so I'm very excited. I'm finally here.
I am so glad to have you here. I should not have waited that long, but it was worth it.
Yes, thank you.